Okay, I just skip this example because the example for log here, before we discuss about this one, let's discuss about the power law. Okay, the power law, the process is almost similar with the logarithmic transformation function because the shape is almost similar. The difference is that you know, whether you want to have for example, if you have a, okay, this is the equation, okay, for power law transformation function, and then c is just a constant, you can set that one. But in this example, let's assume that c equal to 1, and then the one that determine the shape of the power law transformation function is this gamma. Okay, if this gamma is changed, meaning that if you are set the gamma which is less than 1, then it will become a roots transformation function. Then if you increase the gamma ray which is more than 1, then you become a power root transformation function. I'm sorry, the power transformation function. Okay, the nth power transformation function is meaning so that 1 is at the center there. If you increase more than 1, the curve is going toward this direction, and if you set the gamma less than 1, it going into that direction, meaning that if you assume this is the terminology is similar to the logarithmic, meaning that the one which is the gamma which is less than 1 will become your log. Okay, but if you put the gamma more than 1, it seems like your anti-log or inverse log. Okay, the shape of the, but I mean is the shape, okay, the shape of the transformation function. Okay, the explanation here is almost similar that what I've discussed in power law transformation function. Okay, you can see that if you set a gamma which is less than 1, okay, which is less than 1, if you talk about less than 1, is like your if you go to into this slide, is like your log. Okay, it's like your log, so the shape is maybe something like this. Okay, and then if you for gamma less than 1, narrow range of dark input is mapped to the wider range output, while wider range bright output is mapped into narrow range of, you can see over here, even though they are using the word narrow range of dark input. Okay, and then you have a bright input there. The statement here is almost similar with this one. This one, they are using the low input, and then you're using the high input. So that's why in our discussion over here, okay, in our discussion over here, in our whiteboard over here, I use two words there. I use low input, and another word I use a dark region. So why I use another word there? Because of that slide. The slide explain about the power law, because now the power law, okay, they are using the dark input, or in as a previous slide they use a low input there. Okay, so narrow range of low input is mapped to wide range output, while the wider range of bright input, okay, I also can put it as a high input there, that map is mapped into narrow range. Okay, similar to the, if you talk about the gamma more than 1, because its work another way around, is opposite from the gamma less than 1. Okay, so that's why these two statement also you can use the previous discussion, okay, what we have discussed in the whiteboard there. Okay, again, why I said like that, because the power law is almost similar. So you can separate this one into, you know, a dark input or dark region. Okay, and this one is your bright input. Then if you map by using which is this one is gamma less than 1, this one is gamma more than 1. Okay, then this one, if you process at the dark input over here, it will map the very narrow range there, okay, into wider range, okay, into wider range over here. So if you talk about the gamma more than 1, then it's map very wide range there into narrow range there. Okay, it's another way around. Okay, so that's why I said even we have two type of transformation function, the purpose or the characteristic is almost similar between the logarithmic transformation function as well as power law transformation function. So that's why I skip about discussing about this example, because this one involve some Fourier transform or frequency domain. So I just directly discuss about the example in the slide that talk about the power law, because the power law you have another transformation function examples there. Okay, this is one of the example that you can see how you can use a power law transformation function. Again, you can see this is an example of magnetic resonance image of the spine. Okay, it's a fractured human spine, but you can see that this is the input image, and of course this region is very dark and it's very difficult for radiology to observe the characteristic of fracture of this human spine. So one way you can enhance this image is by applying the power law transformation function, but you don't know which one is the best. That's why here there's a process of try and error. First they are set C is equal to 1, okay, same as this one, C equal to 1, but now they are varying the gamma to see which one is the best. Of course, if you want to see the detail about the something which is belong to a dark region, you must not compress the range, but you must stretch. Okay, you must stretch the range. So that's why the suitable gamma power law transformation function that you need to use is when the gamma is equal or less than 1. Okay, so back to our discussion in here. Okay, our whiteboard there. Okay, if you talk about power law, if you want to see information that belong to very dark region, you must scratch the dynamic range. So that's why the suitable thing you need to use is actually when the gamma is less than 1, because when the gamma is less than 1, the very narrow range here, okay, is stretched, okay, is scratched. Okay, what I mean by stretch is stretch. Okay, you are stretching the dynamic range from the narrow range into wider range. So meaning that now the information is more obvious, because now you have a very wide range of possible color as compared to the input, because the input only consists of small number of color because of the narrow range. So that's why if you want to enhance something which is at the dark region, it's better for you to use the power law transformation function where the gamma is less than 1, or if you want to use a logarithmic, it's better for you to use a log transformation function. Okay, but of course it's better to use power law, because power law you still can tune the gamma, then you can adjust the curve, then you can find the best curve that can represent the output that you want to see. Okay, that is what happened at these examples. You can see that they try to vary the gamma. They try 0.6, which is this one, and then 0.4, which is this one, and 0.3, which is this one, and then based on the observation they find out 0.3, which is this one, is better. Okay, it's the best to be considered, because now you can see that the part there is very detailed. Okay, from dark side here become very bright, and you can see a lot of details there. And then of course lower than that, okay, means if you more than that, then it's wash out the look, means that you see the background also become bright, which is not good. Okay, the one that we don't want to improve, we should not improve that. So that is okay, you can see that is how image enhancement work. There's no the right work, there's no suitable techniques there. Which one is better is based on the subjective observation. If you find out this one is better, then you can select the gamma ray, the gamma that equal to 0.4, but some people might say this is better, then they usually choose the gamma equal to 0.4. So it's a very objective or subjective observation there. So that is the difference between image enhancement and image restoration that you learn after this, because if you talk about enhancement, this is how the way we evaluate the performance of the system. Is very subjective process. Okay, so this is the same image there. Okay, this is another example. Okay, now this is the application of image. This is the input image from the aerial view there. Assume that this image is taken by using drone. Of course, this is one of the example example application of image processing in remote sensing. Okay, the one that that have been applied in other school. And then of course by having the aerial view like this, of course you have a cloud there, very bright, and it will produce the bright image there. Of course you with this bright color, with the bright region like this, is very difficult for people to see information on the ground there, on the ground side there. So that's why but now our case over here, we having a very bright region. Okay, very bright region. So in order for you to get the information where actually the case is bright region, and then you must stretch the narrow range of bright region so you can get more information. So in this case, if you want to apply the gamma transformation function, the suitable if you want to use a power law transformation function, the gamma that you need to choose must more than 1. Okay, what is the reason behind that? The same reason that we discussed before. So if you talk about the power law, if you want to scratch the narrow range of the bright image, okay, into the wide range at the output side, then it's better for you to use this one, the blue one, which is the gamma more than 1, because this is the one that can, stretch the narrow range like this. Let's say this is the narrow range. Okay, in the bright side, it's a very narrow range, but on the let's go this part. Okay, this one. Okay, very narrow there, but on the output side, it become very wide. Okay, it's very wide there as compared to the input. This one is bigger than this one. Okay, this one is smaller, very narrow, but at the output side it become very wide because of the characteristic of when the power law transformation function using the gamma more than 1, it will stretch at the bright input from the narrow into wider range. So that is where you can see this example. They are using the gamma which is more than 1, but now you need to use a try and error. Still you need to use a try and error to find the best. Okay, this is a very subjective process again, because of image enhancement always use a subjective evaluation process. Okay, so this is input image. This is the gamma equal to 3, this one is the gamma equal to 4, and this one is gamma equal to 5. And from here you can find out that this one is better because it's more, if you apply more than 4, which is 5 for example, now it's become more and more dark there. Okay, meaning that okay, this is the advantage of applying the power law. If you want to improve on the bright side, actually you are actually downgraded at the dark side. Okay, that is happen because of the shape or the characteristic of the power law of transformation itself. Okay, you can see over here, if you want to apply this one, okay, yes, you are improving at the bright side because everything in the bright you will stretch, but everything in the narrow and in the dark input you are compressed, or you are narrowing down from the wide range into narrow range, meaning that the dark region will be compressed and more information lost, but you are stretching the bright informations. That's why you get more information on the bright side, but you lost information on the dark side. Same goes to the gamma less than 1. you are enhancing or you are stretching the narrow range of the dark side, but you are actually compressing the input, the bright input. So now you are narrowing and lost information at the bright side. So that is why it's it's actually is depend on what application you want to solve. Okay, if you talk about um, finding the information from finding the information um, from the dark region, or you want to get a detailed information in the dark region, then you need to choose um, the log transformation function, which is gamma less than 1, and of course you are sacrificing the bright region inside the same image. Same goes to this one. Okay, because this one we want to improve on the bright side, so you are stretch the region of the bright side, but you are sacrificing the dark part, okay, the dark region. So that's why you can see certain part, like say this one. Okay, now it's become the dark part will become more obvious dark there, more blacks there. Okay, more information there, might be there's some information there, but after you applying this power law transformation function, you will lose the dark region, but you manage to maintain the bright region. Okay, so I hope you understand about this is the advantage and the disadvantage about power law as well as logarithmic transformation function. Okay, if you want to improve on, actually both have the same characteristic, and so that's why you have the same advantage and as well as same disadvantage, because both will, you know, if you choose the curve in that direction, you are improving the dark side, but if you choose the curve in that direction, you are improving the bright side and you are sacrificing the dark side. Okay, so that is the summary of logarithmic transformation function as well as power law transformation function.